Section 7.3 covers logarithmic functions. For a lot of you, this is the first time you're ever hearing about logarithms, or at least getting to know what they are. You probably saw them a little bit on the ACT. I would assume hopefully you saw them a little bit before the ACT. But if you didn't, you probably saw them at least on the ACT. You probably saw them a little bit, or heard of them a little bit from other classes. But if you don't know much about them, that's what we're here for. That's why we're covering them in this video. Okay? Logarithmic functions are basically inverse function for, or the opposite of exponential functions, if you will. So what we're going to do in this video is just kind of learn how logarithm is written, how it's written, what it means when it's written that way. And that's about it. We're going to practice some of the properties in section 7.4, go over them in that video. But a logarithm is an exponent to which a specified base is raised to obtain a given value. Again, it's the inverse operation for raising a base to an exponent. We're going to write exponential equations in logarithmic form, and we're going to do that vice versa. We're going to try it both ways. All right, so here's kind of the meat and bones of exponential to logarithmic equations. So an exponential equation, some number to some power equals some other number. And then a logarithm says log in it, with the little subscript as a base. We call that the base of the logarithm. The number inside the logarithm, and then equals some value. But this logarithm is just basically a rewritten version, if you will, of this exponential equation. So let me give you an example. There's plenty others that will do. But let me show you kind of what this really looks with an actual problem. So let's say I have 7 to the second power equals 49. We know that's true, right? 7 squared is 49. All right, in this case, I've made 7 my b value, my 2 the x value, and 49 the a value. So if I wanted to convert this into a logarithm, this would be log, and the base value, which is the same as this b value, which in this case would be 7, my a value, which would be my 49 in this example, equal to x, which x comes from the exponent, which is 2 in that last example. So this is how you'd write 7 squared equals 49 as a logarithm. There's plenty of other reasons why you'd want to do this, but we're not really going to talk about that here. We're just going to get the nitty-gritty of this and then practicing how things go, how things convert from one form to another. So here's how I remember at least the placement of all these numbers. So each of these has 3 numbers. And you can think of these numbers reading it from left to right. So for the exponential form, 7 happens to be the first number on the left, 2 happens to be the second number, and then 49 the third number. When you rearrange it and you put in the logarithm form, 7 is the first number, 49 is the second, and 2 is the third. So in terms of their positioning, the only position changes or swaps was the second and third. 7, which was the base of our exponent, which is the first number there, happens to be the first number written in the logarithm as well. So its position in terms of being first didn't switch at all. So that's how I can remember where the 7 goes. And then the 2 and 49, as you can see, have switched. Where 2 was the second number, 49 was the last, and now 49 is the second number, and 2 is the last. So that's just kind of an easy trick to remembering the positions. All right, you can see it again here with 2 to the 6th power equals 64. 2 is the first number. Again, the first number doesn't switch positions, so 2 is also the first number in the logarithm, making it the base of the logarithm. But you'll see that the 6 and 64 have switched their roles. All right, so we just looked at 2 to the 6th power equals 64. We're going to try a few other examples just to get more practice. So the next example, 4 to the 1st power equals 4. Again, just to keep in mind, in terms of the position of these, if we want to write this as a logarithm, the first number, which is 4 in this case, is still the first number in the logarithm, so that 4 becomes the base of the logarithm. And then the 1 and the 4 essentially switch their roles. So 1 becomes the last number, 4 becomes the second one. So 4 would be here in my logarithm, then be equal to 1. So that's the way you'd write 4 to the 1st power equal to 4 as a logarithm. Log base 4 of 4 equals 1. Another example would be 5 to the 0 power equals 1. Again, if you're going to write this as a logarithm, 5 being the first number would be the base of the logarithm. And then 1 would be the second number and be equal to 0, because the 1 and 0 switch their positions in terms of what's second and what's third. So it's log base 5 of 1 equal to 0. The next one, even with the negative exponent, it still works. You'd have a log, the base would be 5, since 5 is the first number. And then it would be of 0.04 equals to negative 2. All right. And then one more. 3 to the x equals 81. Again, 3 being the base, being the first number, doesn't change, but x and 81 switch. So 81 becomes the second, x becomes the third. So that's just, again, learning how the positions are for logarithms and kind of how they're equated and how they set up. You can do this backwards as well. If you have a logarithm, you can write it in exponential form. So this logarithm, you can see 10 is the first number there, which would be the first number in our exponential form. And then 2 and 100 switch. So 2 will be the exponent, and then 100 would be behind the equal sign. Of course, you can see that that's a true statement. 10 squared does equal 100. Hopefully, you get something there that makes sense. We want to say 10 to the 100th power equals 2, because we know that's not true. All right, so log base 7 to 49 equals to 2. This one would be 7 squared equal to 49. We kind of already saw that one earlier in the video. For this one, we have log base 8 of 0.125. That'd be 8 equals to negative 1. 8 to the negative 1 power equals 0.125. All right, skipping ahead a bit, this would be 5 to the first power equals 5. Again, this 5 and that 5 are the same, but the second 5 and the 1 switch in terms of their positions. And again, 5 to the first power equals 5 does make sense. And we have 12 to the 0 power equals 1. So now a few general rules to remember. Logarithms are logarithms, but they are based on exponents. So any rules that we have for exponents do apply to logarithms as well. So notice this first rule. If our logarithm's base and the number in the logarithm are the same, so let's say logarithm with base b of b, that will always equal 1. An example of that would be a log base 7 of 7 would equal 1, because these two numbers are the same. Like, again, that's essentially saying that 7 to the first power equals 7, which is always going to be true. Because if you take any number to the first power, it's always going to equal that same number. It doesn't matter what it is. 7 to the first power would equal 7. X to the first power would equal x. 18 to the first power would be equal to 18. So because of that rule is always true, anytime we get two numbers here in our logarithms that are the same, it would always be equal to 1, because 1 is the exponent that would make them the same. So again, another example you can have would be like a log base 19 of 19. That would always equal 1, because the two numbers here are exactly the same. The other rule, log base b of 1, would always equal 0. So in this case, it's not going to matter what the base is, because any number you put in there, if we take it of 1, it's always going to equal 0. And the reason for that is if you put this in exponential form, it'd be b to the 0 power equals 1. And that's true every time. It doesn't matter what b is. Anything to the 0 power always equals 1. 5 to the 0 power equals 1. 19 to the 0 power equals 1. X to the 0 power would always equal 1. So any logarithm with a base, doesn't really matter what this base is. It could be 7, but if it's of 1, it would always be equal to 0. And some test questions they like to ask to try and trick you, even though they're not hard questions, would be questions like, find the x in this logarithm. We might have the logarithm with base 9x equal to 1. And it'd be like, find x. But if you notice, if this equals 1, that would mean that these two numbers would have to be the same. Therefore, x would have to be equal to 9. So it's one of those questions that if you remember this property, it's going to help you save a lot of time, answer really quickly. But if you forget the property, hopefully you can probably change this in the sense that this is the same as saying 9 to the first power equals what? And you can always figure it out that way if you didn't remember the rule. But remember, you still have to know the ins and outs of how to write a logarithm in exponential form and vice versa. And the last thing, before we end it here, is a common logarithm. A common logarithm is any logarithm with a base of 10. And it's called a common logarithm because we don't typically see the base. You'll see in these examples, it just says log 5. It doesn't have a base here. That's because if there is no base, we assume that base to be 10. And that's what we'll use common logarithms for. So log of 5 is the same as saying log base 10 of 5. Log of 8 is the same as saying log base 10 of 8. And log 1000 would be the same as saying log base 10 of 1000. So if you don't see a base here, you assume that base is 10 because we're using common logarithms here. These are kind of just what you'll use most of the time when you're working out equations, which we'll be doing in later sections. But just know that for now. It's kind of like one of the simple things in math. We use them so much that we don't want to waste our time writing a 10 if we can just create a shortcut where we don't have to write it. All right? We'll end it there, and we'll see you in the next